So this is the first video of a sequence on handling big data with PCA. Now, big data in risk and asset management is a novel topic for mainstream finance. In this video, I'm going to talk about one often applied non-supervised learning technique, the principal component analysis. Imagine you manage a portfolio with 1,000 or more assets. It's to be expected that several of these assets share very high asset return correlations. This gives rise to multicollinearity problems, which, for example, won't allow you to determine the minimum variance portfolio or any other efficient portfolio. In addition, you won't be able to invert the covariance matrix. Also, standard estimation techniques such as least squares or maximum likelihood won't be applicable. So there are a ton of numerical problems that you run into. In addition, from the CAPM and the development of linear factor models, it's intuitive that there might be a few set of factors out there that are responsible for most of the portfolio's unexpected return variations. And in addition, you get compensation only for these systematic risk factors. So a principal component analysis is one way to back out a set of risk factors that are responsible for most of the unpredictable return movements in the underlying factors. Such risk factors are also called statistical risk factors. Now, in a nutshell, PCA, the short version for principal component analysis, is an unsupervised learning tool to reduce the dimensionality of correlated data without giving up a significant amount of information about the data's second moment. So assume the return panel has dimension t times k, where t is the sample length and k is the number of assets. In total, k principal components of length t times 1 each perfectly represent the original t times k data. Each principal component is pairwise uncorrelated and constructed to capture maximum variance of the original underlying data. So the goal of a PCA is to represent stationary data X with dimension t times k and a non-diagonal k times k covariance matrix, sigma x, such that, first, the transformed t times k data x tilde has a diagonal k times k covariance matrix, which we call sigma tilde x. This says that each t times 1 element of x tilde is pairwise orthogonal to the other factors. And second, each orthogonal factor explains the maximum variance possible. And third, x tilde contains exactly the same information as x.